And I know it's early, it's first presentation, so people will be shuffling in, but day's got to get going, so here we go. My name is Peter Landon. I work at BTI in the CTO office, and today I'm going to be talking to you about DWDM and packet optical. So we'll start with packet optical, and what it's all about is standardized services being offered, and it's in a number of different forms. The first one being E-line services, which is essentially point-to-point for virtual private lines and Ethernet private lines. The second type is the E-LAN, which is a multi-point service, transparent LAN service and multi-point layer 2 VPNs. And then we have an E-tree service, which is a rooted multi-point layer 2 VPN. And this could be used for broadcast networks or anywhere where you don't want communication between the leafs and the network. And finally, we have an E-access service, which is for wholesale access and access Ethernet private lines. A key to standardized services in carrier Ethernet is the ability to deliver multiple services, different services, and managed 10 gig wavelength services all on the same network. And this provides an economy of scale to the carrier and allows for a flexible configuration environment. Service bandwidth scalability is also a key factor. For any user network interface or UNI, there's multiple interface speeds from 10 meg to 10 gig. And within each Ethernet virtual circuit, there's different bandwidth offerings, 1 meg to 100 meg in 1 meg steps, 1 meg to 1 gig in 10 meg steps, and 1 gig to 10 gig in 100 meg steps. And within each Ethernet virtual circuit, you've got different bandwidth profiles. The CIR is the committed information rate, and that's your guaranteed rate to the customer. An excess information rate, or the EIR, is for bursts, short-term burst accommodation. To be effective in the WAN, Ethernet needs to have a high availability component, and G8032 was introduced to bring ring protection switching to Ethernet, and it allows setup of protected rings between nodes, and if there's a failure on a link, there's a protected path through the ring, as you can see in the diagram. These are necessary in the WAN to mirror what Sonnet SDH has provided in the past. I'll get into a little bit on latency of the network. There's actually 3 components to latency within the carrier Ethernet. The first is propagation latency, actual propagation of the light through the fiber, and it's more significant than you might think. It's approximately 5 microseconds per kilometer, and the fiber itself in your network planning is never as the crow flies. There's always a significant portion, up to 10%, for rights of way and patch panels and etc. So we see an example here of 3 nodes with 2 access points, and the latency can be approximately calculated by just simply adding up the lengths and multiplying by the latency of 5 microseconds per kilometer. And in this case, we have about 158 microseconds. The next component would be serialization latency, and this is the delay in getting a packet from start to finish through the wire. And it's a function of, obviously, of the speed of the interface and also the packet size. So smaller packets take less time, and longer packets take longer time. And as the rate of the interface increases, of course, the time will decrease. Finally, you have switching latency. So in a traditional SDH or Sonnet network, you can see for a TDM fabric, your latency through the switch is between 125 and 150 microseconds. You might notice 125 being the 8 kilohertz frame boundary. IP MPLS varies between 500 200. And then carrier Ethernet between 10 and 20 microseconds. And this is primarily due to the fact that you're not having to buffer a full frame of data. You can switch on the packets, which are much smaller. So when you add it all up, you get in this particular example, where we've got 10 gig links between the 3 nodes, 100 meg links at the customer, a total round-trip latency of around 400 microseconds. And this is, there's 2 examples of it. There's a test set and a 1731 output directly from a test set that confirm the estimates that were made from the fiber lengths and the calculations that were done. So what does this all mean for latency? The fiber route is usually the major contributor, depending on the span length. As spans increase, obviously the latency is going to increase and become more of a major component in the total equation. Serialization is also a component, but again, as the rates are increasing, the latency due to serialization is actually decreasing as a component, or being dwarfed by the fiber latency. And then, of course, the switching technology is a key differentiator in the sense that with packets, you're not buffering a full frame, you're switching at the packet level. So the latency through the switch is much, much less. And so we also have to be able to monitor all of these, this component as well as others. And service management and SLAs are a big part of carrier Ethernet. And when you think of traditional networks on an SDH, they're very rich in performance monitoring and OAM because you've got the overhead bytes available to do what you like. They're not there for Ethernet, so other standards were introduced to provide these features. So without the overhead bytes, the service management is done through messaging. There are what are called maintenance endpoints and maintenance intermediate points, which are blocks within the nodes done in hardware which allow you to do messaging for performance monitoring. So you have connectivity fault management, which is essentially continuity check messages between MEPs and MIPS to indicate failures or unintended connections. You've got link trace, which is equivalent to a layer 2 trace route, which is essentially messages between maintenance endpoints, and they report the MIPS and MEPs that are in the path. And we also have loopback, which is essentially a layer 2 ping, which is messaging between the endpoints, the maintenance endpoints. So these combined create the 3 keys to this SLA performance monitoring: performance, utilization, and availability. So on the performance side, Y1731 defines methods to measure latency, jitter, frame loss. And then the utilization, it can be measured as well through special packet injection, which is then looked at statistically to ensure you've got it's basically the bandwidth throughput of your link. So in order for a customer or a service provider to test their network, different test methods have been standardized, which allow measurement of or define specific tests that need to be run for throughput, latency, and frame loss. So the first one was RFC 2544, which was introduced by the IETF, and it deals with maximum bandwidth flows through the network and measures the throughput and latency. Y1564 was introduced to allow multiple service measurements simultaneously. It's also robust from a service point of view. It can allow different flow types, different specific flow types to be measured. again, all simultaneously. So it's a very effective measurement. And these normally from the tester will output an automatic report. So advantages of the packet optical carrier network, carrier Ethernet network, flexibility. The ability to offer 10 gig wavelength services on the same network is a huge benefit. There's simple service activation as well, which is part of the network management system. And the capacity of the network is also easily expanded if you have a DWDM network in place, which we're going to go through next. And reliability, which used to be a concern in Ethernet networks, is now been taken care of with protection switching and rings through G.8032. The latency is very good through the packet network because of the smaller packets and the more efficient switching fabric. And the SLAs provide performance guarantees to the customer. In addition to those, we didn't talk about it, but synchronization, SyncE is also a capability to provide similar synchronization capabilities to the traditional TDM network. That's available. And all these put together can offer a lowest cost per bit through the use, again, of DWDM. So let's talk a little bit about DWDM. What we have here is a standard point-to-point system with the various components contained. I'm going to speak about each one individually. I'll say I haven't included ROADM components in this presentation. It's a presentation on its own, which I'll probably give at some point. But it's an extension of all of the components that we'll go through today. So the first component is a transponder, and essentially what that is an ability to convert wavelength from one wavelength to another. There may be some retiming done as well. At some PM performance monitoring would be available at that element as well. Second, it would be amplifiers, and we'll talk a little bit about that. Third is the add-drop filters, or the add-drop MUX, which allows individual wavelengths to be added or dropped at each node. Finally, dispersion compensation. We'll talk about how dispersion compensation is used in the network and how it will reverse the effects of chromatic dispersion on fiber. So let's start with service modules. As I said, the transponder is a one-to-one element. It's generally electrical, so it'll have a retiming element. It'll do an electrical optical conversion. And what it's normally, or what it can be used for, is to take a gray optic, say from a router or a switch, and convert it to a specific wavelength or specific channel that can be transmitted in the DWDM network. The muxponder, on the other hand, is similar, but has multiple inputs, multiple protocols as well, and will combine these multiple clients into a single wavelength. Again, this is done optically, done electrically through GFP or some sort of mapping protocol. The predominant or a very popular use of a muxponder today would be to take 10 gig Ethernet client and an 850 nanometer client from a router, let's say, take 10 of them, wrap them in OTU2, and then combine them into an OTU4 container and send them out as a single wavelength in a coherent fashion. That's a use case that's being used quite extensively for data center interconnect. On the transceiver side, these are the plugs that are used within the transponders and the muxponders. Typical line rates are 2.5 gig, 10 gig, 100 gig. And the form factors vary. You can see the CFP there, which is being used now for coherent 100 gig. QSFP Plus, which is the 40 gig form factor. XFP, I'm sure, no doubt familiar with that. It's a 10 gig form factor. And SFP Plus now, which is pretty much overtaken XFP. The type depends on speed and reach. 850 nanometer would be a client interface running on a multi-mode fiber, whereas the 1310, 1550 would be running on the line side. The transceiver has a transmit power spec and a receive power sensitivity. So on transmit, it'd be anywhere from -3 dBm to a +1. And the RX it does vary depending on the transceiver, from anywhere from -25 to -5. So on the DMUX side, this is where all of the wavelengths come together, and this is kind of the heart of DWDM. And if you think back to your high school physics days, you have think of a prism, and when light traverses from one medium to another, it actually changes speed, and it's refracted. And the refraction occurs differently for different wavelengths. And it allows you to take a stream of white light and split it into its constituent colors with glass. So this principle is used for the MUX-DMUX, and it allows you to take all of the colors that you've defined with your transceivers, combine them into a single fiber carrying the multiple wavelengths. Each port on the transponder or the muxponder would correspond to a different wavelength, allowing you to do multiple services over a single fiber. So out of the MUX-DMUX, it goes into an amplifier. Here I'm showing an EDFA amplifier. What an amplifier does is quite simple. It takes an optical analog signal in and amplifies the amplitude. Similar to your home stereo or your iPod, you turn up the volume, you can increase the amplitude of the signal. There's two common types of amplifiers. The first, most common type is the EDFA, the erbium-doped fiber amplifier. It's simple to deploy, good characteristics. It can be fixed gain or variable gain, and it's widely used. The second type is the Raman amplifier. It's generally used for longer spans with higher loss, for longer distance transmissions. It's higher cost, uses more power, but it has a capability to drive a long span. So they'll be used together in combination for different span lengths to achieve the OSNR that is required for the network. So common application of amplifiers. Traditional optical transmission network, you've got a couple of nodes with repeaters. They could be optical repeaters placed every 60 kilometers. And when you introduce a new service or a new increase in bandwidth, you need more regenerators. If, on the other hand, you implement wave division multiplexing, you can have multiple services, and rather than adding physical fiber, you add new wavelengths. These wavelengths can be combined into a single fiber through the MUX-DMUX, and instead of 16 regens, you can replace the 16 regens with 4 optical amplifiers. And instead of all those fibers and all the patch panels and all the patches, you've got single fiber between them. So within the fiber, there are loss effects, and one of the big ones is chromatic dispersion. Chromatic dispersion is counteracted with elements called DCMs, or dispersion compensation modules. So chromatic dispersion happens when you have different wavelengths traveling through the glass fiber. As we mentioned before, different wavelengths travel through the medium at different speeds. And as they travel down the fiber, I've got a good animation here. As they travel down the fiber, because they're traveling at different speeds, the wavelengths will peak closer together, and the pulses will start to overlap. The receiver has a hard time to distinguish. The colors become somewhat blurred, and the longer the distance or the higher the bit rate, the worse the spread becomes. So DCMs were introduced to reduce this effect, and essentially what they are is it's a special type of fiber that has a negative dispersion ratio. So it essentially reverses the effect of the chromatic dispersion that's occurring on your fiber plant. And a DCM itself is simply a module which is a loop of this special fiber, and it's specified by length. So if you have, in this case, we've got a length of fiber between an amplifier. The chromatic dispersion has reached a maximum amount after a certain length, so a DCM is introduced at that point in the network. The reversing effect of the DCM, that loop of fiber, reverses the chromatic dispersion and can actually make a negative spread. Then it's going through the fiber again, and the compensation, it has to be introduced at the various lengths. So wherever you have a node or an intermediate amplifier stage, you can introduce the DCM to counteract the effects of the chromatic dispersion on that fiber length. So you would specify the DCM to be for a 200 kilometer length or an 80 kilometer span. And simple plug, it's a passive element that achieves that compensation. So now we'll get into a little bit of the troubleshooting on the transmission layer. One of the first problems that we see quite a bit is an issue of a saturated amplifier. This is when you drive the input to the amplifier with too high a power level. Every amplifier has a typical gain curve, and there's a portion of the gain curve, power in, power out, that's flat. So, but every amplifier also has a nonlinear portion. So if the input power gets too high, there'll be a clipping effect, and it's again similar to audio amplifiers. If for a 10 gig channel, a good rule of thumb is a 6 dBm per channel. And every time you double the channel, you're increasing the power by 3 dBm. So you can use this information to match your number of channels to the amplifier gain curve and make sure that you stay within the linear range. The other problem that you might encounter is the fiber type. SMF28, a normal type of fiber, most DCMs are compensating for this type of fiber. If you're not using that fiber type, you may be overcompensating for dispersion using a standard DCM module. Also, zero dispersion shifted fiber isn't great for DWDM, so if you have that in your fiber plant, you want to know about it. So otherwise, you'll be trying to debug it. One other area that's useful for debugging degradation of the fiber network is using a prefect bit error ratio. So if you're familiar with FEC, it's forward error correction which is an algorithm used to actually correct errors in your data. And if you can monitor the errors that are happening before the fact, you can get in front of problems before they actually affect customer data. So bit error ratio, just as a quick summary, is the number of errored bits received over the total number of bits received. So as an example, 3 to 10, if you have 3 to the 10 to the negative 5 bit error ratio is 3 bits in 100,000 that are transmitted in error. That's a high bit error ratio. So if you look at the graph showing the correction that the FEC provides, there's a steep cliff that happens where the FEC is no longer effective. And you don't want to be sitting at the edge of the cliff in your network where you're going to, any further degradation is going to cause a customer impact. So if you can monitor the errors that are occurring and the increase in the errors pre-FEC, you can make the corrections to your network before the customer actually even sees any errors. And if you're monitoring bit error rate, a rule of thumb for measurement time is that for 99% confidence in the bit error ratio, you have to count 4.6 times the reciprocal of the bit error ratio, and that's a number of bits. So for a bit error ratio of 10 to the minus 8, you'd have to monitor 4.6 times 10 to the minus 8, or 460 million bits. And so you can calculate the time that you're going to need to monitor based on the rate. Now the number one culprit that causes troubleshooting calls and FAE calls is optical back reflection. And if it gets bad enough, the amplifier actually thinks it's driving an open connection and it will shut down. The main causes of optical back reflection, well, I should say there's always some optical back reflection in any fiber transmission, but the ones that, when it gets to size that causes problem, it's caused by bad or dirty connections, poor splices, too many patch cables or patch panels, or an old fiber with too much inherent back reflection. So obviously solutions to the problem: cleaning of fiber connections, consolidating patch panels if possible, and checking that all connections are clean and tight. The back reflection has to be minus 24 dBm or less at the amplifier. So for testing, you can see here we've got a screenshot from a fiber tester showing a clean connection and a dirty connection, and we're also showing a trace of an OTDR test. OTDR is optical time domain reflectometer, and it's used to send a pulse of light down a fiber, and it measures what comes back. And these measurements can tell you in meters where these discontinuities are, and they can give you a heads up as to where to go, where to drive, what to clean. So you can see here that you can see the spikes of back reflection and the bottom scale in meters. So there's a back reflection at less than 25 meters from the source, from the tester, that's introducing that large back reflection. And at the points 2 and 3, those are also dirty connections that at close to 200 meters. So the connector design in the last number of years has come a long way, and it's not really the large point of problem now. But what still remains a problem is the pristine end face and actually contamination between the connections. So this little animation is showing you what happens with the reflection, with the the contamination causing the back reflection. And again, contamination, the number one source of troubleshooting in our company, and the number one source of calls. We've had lots of people on site, spending lots of hours with the result being dirty connections. Inspecting both sides of the connection is the only way to ensure it will be free. The patch cord is pretty straightforward. You can plug it in. But the bulkhead is actually where a lot of the issues happen. So it's important to also test the patch panel. And it always results in a need to have the fiber cleaned. OTDR can also be useful in finding fiber aging and macro bends. So as fiber is handled within a patch panel or in a fiber plant, as it's accessed and plugged and unplugged, these bends can occur. And rather than spikes, they show up as a little hill in the OTDR trace. You can see they are wavelength sensitive as well. So at 1310, the bend has little effect on loss. At 1550, it's a dB, and at 1625, it's significant at 3 dB. Obviously, the tighter the bend that you have in the fiber, the worse the problem is going to be. So beyond basic BERT testing, we've talked a little bit about this, but it applies across the DWDM network. You've got RFC 2544, which is a framework for measuring throughput, loss, delay, and jitter. And it's performed across all the frame sizes to a maximum bandwidth. Y1564 is the newer standard, and it allows you to do multi-stream tests with pass or fail for different service configurations. Each one is tested individually, and a report can be issued automatically. It takes into account CIR and EIR, which 2544 does not, and it also will compare to the SLA that you have in place for frame delay, delay variation, and loss rate. So, in summary, we've talked about packet optical and carrier Ethernet and impacts of latency, how things are measured with your SLA, and the different test methods that can be implemented to ensure that the network is performing to the specs. And we've gone through DWDM basics, the building blocks, muxponders, transponders, add-drop muxes, and amplifiers. Some of the troubleshooting tricks that can be used and tools, and some of the test methods that we use at BTI. That's all I have. I'm open for questions if there are any.
Hi, Colin McIntosh, SIG. Do you have any recommendations on how to, I guess, prevent dirty fiber in your network? I feel like, in my environment, we're always chasing down, dirty fibers and errors in our network.
Yeah. Well, exactly. I mean, it's the number one thing we look for, and even, we've got customers that say, we've checked all the fibers, we've cleaned them all, and there's always that one patch panel that got missed or didn't get cleaned properly. So as far as keeping the dirt out, I mean, we just have a huge number of fiber cleaning tools everywhere, because I think what happens, I mean, even in our lab, is that people look around and these things, the little green boxes, they have a tendency to walk away, and If they're not there, people, okay, I don't have one, they just plug it back in. If there's one around and it's accessible, I think that on an ongoing basis, keeping the fiber clean is the way to go.
Gotcha. Thanks.
Yeah, no problem.
Yes, Bill Goldstein, retired AT&T, but asking the question here and representing only myself. For RFC 2544 and ITU-TY 1564, extremely desirable standards. In your experience, though, how widely have the standards been implemented in DWDM vendor equipment and carrier networks as well?
So it is a challenge, I will say. I mean, there are changes that have to be made in the hardware to be able to do the packet measurement that's required, and sometimes it's using merchant silicon in the equipment is just not available. Or if you have legacy equipment, some of the blocks just aren't there. So in our experience, we've tried hard to implement the tests, and we've had demands from our customers to do so, I think it depends on the sophistication, I hate to say it, of the customer, and whether their knowledge base. But certainly, I would say the majority of the customers demand the tests to be in place and demand us to support the tests.
Okay, but if the customers demand it, can the carrier supply it? I mean, suppose someone is out there writing RFPs for large-scale DWDM or applications running over DWDM. You don't want to write in something ideal, which almost no carrier can provide, yet you want to write in standards which can be reasonably met by a responsible and robust carrier. When you're doing that, I'm sure many of you in here, perhaps have been, at times facing RFPs, which are at times, overwritten for standards that don't exist in reality in deployed networks. I'm just trying to get some idea of what, with these two standards, realistically exists in deployed networks.
Well, for the big ones for us, and you're right, it's not, I think the standards define a whole host of elements, from packet throughput, packet loss, latency, jitter. For us, there are elements that rise to the top as far as importance go. That is latency is always a big one. Packet throughput is always a big one. Packet drop, we do it, but really the latency is always demanded, for sure.
Okay, well, then, thank you. I appreciate the answers.
Yeah, no problem.
Vikas, AOL, why do you say that the lowest cost per bit is a combination of carrier Ethernet plus DWDM? I'm not clear how you draw that conclusion.
Well, I think that comes from more on the DWDM side, being able to expand your network through additional wavelengths, rather than buying up or using dark fiber for each and every connection.
Okay, thanks.
All right, I guess that's it. Thanks.
Thank you.